In this lecture, we're going to take a closer look at how we go forward with a linear regression analysis. And so the term linear regression and least squares, these terms are often associated with each other in terms of trying to predict an outcome from one or more predictors. And this approach is predicated on developing a model. And when we think about a model is just simply the representation of some real life event. It's not the actual exact event. And so in many instances, we don't actually have access to the real event or a particular population in terms of the data. And so we use small samples to help develop a replica, if you will, of that population or of that event. And so a model is just that. It's a simplified approximation for the relationships between variables in the population of interest. It's simplified to the point where it's good enough to replicate that real event, but not so simple that it loses accuracy. And so the trick with linear regression analysis isn't so much in the statistical procedure, it's in the research design approach. And the challenge is to identify those variables that are related to an outcome that could reasonably be assembled into a model of that event. And it's also important to note that when we talk about linear regression, we are not directly implying any causation. This is an examination of a relationship. So the first model as the foundation for this approach is what's called a deterministic model. And a deterministic model is expressed in a mathematical expression, but it maps the relationship between two variables. Those two variables, we'll just use symbols x and y, in a population where there is no variability or randomness. So this gives us a perfect relationship expression so that if we input a value for x, we will get one and only one value for y. And so you get the one value for y when you enter one value for x. And so the deterministic model is one that is ideal in visualizing a relationship between two variables. Now, the problem with the deterministic approach is that when we actually deal with real data obtained from a sample in a research study, we can actually have different y values every time we enter in an x value. So, for instance, if I enter in an x value of 5, and I use these variables, and I'll describe these in a moment, but if we run the math for a value of x equals 5, I might get a 10 on the left-hand side. Now I run the equation again, and I input a 5. The next time I run the equation, I might get a 12. And so that's the issue when we deal with real data. We don't always get the same outcome when trying to predict the relationship between those two variables. What you see here, these two symbols are alpha and beta. These are two parameters of the model that are fixed values that are inherent to the properties of the relationship between the two variables. So the only two items that vary in terms of numerical value is x and y. And because of that problem with the deterministic approach, the deterministic approach is a very good approach because it provides that foundation for understanding and beginning the process of examining that relationship from a research perspective. That leads us in the direction of this concept called conditional probability. And what conditional probability considers is that we can actually have a number of different outcome values every time we input the same x value. And so that's not necessarily a problem of the model. That is just the nature of dealing with real data obtained from different cases. And so conditional probability basically tells us is that at each value of x, so every time we input an x value, there's going to be a range of y values, and though that range can be described as a probability distribution. So at different x values, we're going to get different, potentially different probability distributions of the outcome variable at different x values. And that leads us to what's called a probabilistic model. And this is what's generated in a regression analysis using either computed manually or computed with a software program. So in the probabilistic model, as opposed to the deterministic model, this accounts for the variability in the outcome at each value of x. So we don't make a perfect, this tells us that we cannot make a perfect prediction in reality, but the regression analysis approach allows us to account for that variability in the outcome at each value of x. And that produces what's called a linear regression function. And a function is expressed as an equation, as you can see here at the bottom of the slide, and we'll get to this one here shortly. But the linear regression function is that equation that represents not a single y outcome at every x value, but the calculated y value is an average value at that x value, at that x input. So at a given x value, alpha plus beta x, this is the right-hand side of the equation, represents what's called the average or the mean of the conditional distribution of y at that x value. So at a given x, the y outcome is considered to be the average value, and then we consider the range of values above and below that y value, very much as we consider in terms of descriptive statistics, we have a distribution of scores, we have an average value, and we have scores that are above and below the average. This is the same concept here. And we change our y of x to what's called, or the symbol uppercase E of y. And this is the expected value of y. So instead of clearly defining y as a function of x, we consider the fact that there's a range of scores. And so we expect a particular y value. And by expecting a particular y value, we keep our mind open to the possibility that it may not be that exact y value. That y value is going to be a representation of the possible outcome of scores at a given x. So this is the expected value of y, which is the average of a conditional distribution of those y scores. And so this, once again, is our foundational model. This is our probabilistic model that looks very similar to the deterministic model, except that on the left-hand side, we're not looking for a single value, but we're looking for an average value. And so this approach now is our foundation heading into a regression analysis. So this models the relationship between x and not y, but the relationship between x and an average value for y, which is our expected value. And to illustrate this, we'll begin with an example here by examining the relationship between annual income and years of formal education. And so based upon this question, many might look at this and wonder, what is our key outcome variable? And I think many would agree that our key outcome variable might be the annual income. And the question here is, can the number of years of formal education influence, not cause, but influence, have a relationship with annual income? Can we predict annual income based upon that? And so we start with our probabilistic model, the expected value of y, which is our annual income. So what can we expect given this relationship on the right-hand side? And because we're using Greek letters here, Greek letter alpha, Greek letter beta, these are once again, the parameters in this model as it relates to a population. And these are inherent, these describe an inherent property, two inherent properties of that relationship and are fixed values. Now, based upon previous research, a researcher might reasonably surmise that the parameters, based upon previous studies and perhaps other theoretical considerations, that the alpha would be, the fixed value would be negative 2,000. And because our outcome variable is annual income, the units here would be dollars per year for our annual income. So our alpha would have to match those units. So this would be negative $2,000 per year. Now, that in and of itself would suggest debt, but this is just one part of the probabilistic model. So we certainly look at the individual parameters, but in terms of predicting the outcome, the conditional probability, we take it as a whole. So with this example, if we have a person with 12 years of formal education through that would take them through high school, we might enter a 12 into the X here, and given these two population parameters, we run the math and we'll come out with an expected value of Y of $58,000 per year. Now, that doesn't mean that a person that has 12 years of formal education will make this much, but based upon our probabilistic model, this 58,000 represents the average income. Not everyone will make this much money. Some will make above average, some will make below average. And so the whole point of regression analysis is to try to get a handle on how much above the average and how much below the average can we now predict with a degree of confidence that our input variable, which is X, will result in. So this is our probabilistic model based on a population. And once again, we don't usually have access to the population. So what we do from a research perspective, we select a much, much smaller sample than what we'd expect in the population. So as a result, we don't know what the value of alpha would be. We don't know what the value of beta might be. This might just be a theoretical approach that a researcher would take based upon theory or based upon previous research. But we don't really know if these two parameters hold for that population. And so what we do then is we take our sample and we develop a prediction equation from the sample. And you'll see here that the prediction equation form is the same as our probabilistic model, except that we're going to input an X value, as we did up here, but our outcome variable is not the Y variable, but what we call Y hat. And the hat, the symbol, is the symbol for the predicted value of Y, not the actual value of Y. So when we have a sample, we have a set of data on X. We have associated data for each case or each person for Y. But what we're going to do is try to predict that Y. And the difference between the two is what we will call error eventually when we get to it. And we also replace the alpha and the beta with lowercase a and lowercase b. These are the parameters in our prediction equation from the sample. Remember, when you're dealing with a sample, you use symbols that are English letters. When you're dealing with a population or a theoretical model, we use Greek letters. So this graph depicts a sample relationship between the number of years of education and annual income and we start with our the foundation for our regression equation based upon the sample. So we formulated that theory on slide number 9, but now if we have real data collected, say, from 30 to 40 to 50 people, we then pivot over to this approach. And so what we're trying to examine, or what we will examine, is the predicted value. So a regression analysis will yield a regression equation. The A here in the regression equation on the graph below, and we'll see this shortly, is what's called the y-intercept. And that is the value of y when the x value equals 0. So if we enter a value for x of 0, this term goes to 0, and all we're left is with A. And we'll see that on the graph shortly. The B, what we will refer to here in the future as the coefficient, which is a fixed value. So A and B are two fixed numbers that are properties of the relationship. The B is specifically the slope of that relation, which is best depicted on the graph below. And so we call A and B regression coefficients, and in a computer software outcome, they will be labeled as such. And so here we have our regression line, and the standard linear regression approach assumes the relationship is linear. So the equations are designed to on the idea that it is a linear relationship, straight line relationship between the two variables. So here we see, just make a visual observation that as a person's number of years of formal education is greater, their annual income will rise as well. And this line is described by the y hat of x is equal to a plus bx. So if we set education in this model to 0, that's where the line intersects the y-axis. And so that y value, or that a value, or that y value is what we would input into that equation. So this is a fixed value. So no matter where you look at the x-axis, a is always going to be this particular value in the equation. The other coefficient here, the b, is the slope of the line. And the slope of the line is quantified in this depiction just simply as the rise over the run. So the change in y divided by the change in x. And so whatever this value is now becomes the second property of this relationship. The first being the a value, the a coefficient, and the second is the b coefficient. So this ends this part of our lecture on introducing the key items for linear regression analysis.